Let's learn about why your code speed actually matters with Big O notation. Your search feature works instantly with 100 products. You ship it. Users love it. Then your catalog grows to 10 million products, and suddenly the same search times out after 30.0 seconds. What changed? Not the code, not the server, just the scale. This is the moment Big O notation predicts before it happens. Big O measures how much slower your code gets as the input grows. It doesn't count seconds, because that depends on your machine. It counts operations. The performance in seconds can be inconsistent, as it depends on many external factors like machine speed. However, the number of operations your code performs scales predictably with your input size. And the difference between a search that does one operation per product and one that does one operation per product is the difference between instant and broken. These growth rates are often referred to as Big O linear or Big O of n and Big O quadratic or Big O of n squared. With 10 million products, linear code does 10 million operations. Quadratic code does 100 trillion operations. That's not slow. That's impossible. Big O notation tells you exactly when your code will break, so you can fix it before your users find out. Big O isn't about measuring speed. It's about measuring growth. Let's see this with 3 different ways to search for a product. First, linear search. You check every product, one by one, until you find the right one. If you have 10 products, you do 10 operations. This behavior is described as O of n, where n is the number of products. The operation count grows in a straight line with the input size. Now, imagine a nested loop. For every product, you compare it to every other product. 10 products means 55 operations. This is O of n squared. The operation count grows exponentially, forming a steep curve. Finally, a hash table. You jump directly to the product using its ID. 10 products, 1 operation. This is O of 1. The operation count stays flat no matter how large the input grows. Now, consider what happens with 10 million products. For linear search, you would perform 10 million operations. For a nested loop, 10 million products would require 100 trillion operations. But for a hash table, it's still just 1 operation. These 3 curves, flat, diagonal, and steep, are the visual signatures of Big O. Once you see them, you can predict which algorithms will scale and which will break. So how do you figure out the Big O of your own code? You count the operations. If your code has one loop that runs n times, that's O of n. If you have a loop inside another loop and both run n times, you multiply them. That's O of n times n, which is O of n squared. Let's see this in action. Linear search uses one loop to check each product. The loop runs n times, so the operation count is n. That's O of n. Bubble sort uses 2 nested loops. The outer loop runs n times, and for each iteration, the inner loop also runs n times. So the operation count is n times n, which is n squared. That's O of n squared. A hash table does constant work per insertion. No loops, just direct access using the product ID. That's O of 1. Now here's the key insight. At small scales, the difference doesn't matter. But around 10,000 items, O of n squared becomes a problem. At 1 million items, it's completely infeasible. Big O helps you see that breaking point before you hit it. You can count operations in your code, predict the complexity class, and choose algorithms that will scale. Big O isn't just theory. It's the reason Google search returns results in milliseconds even with billions of web pages. It's why Netflix can recommend movies instantly for millions of users. And it's why your banking app processes transactions without slowing down as more people use it. These systems all use algorithms with efficient Big O complexity. Google uses hash tables and tree structures to achieve near O of 1 search. This direct access means that no matter how many items are stored, finding one takes roughly the same single step, which is the essence of O of 1. Complexity. Netflix uses O of n log n sorting and filtering to generate recommendations. This recursive division and sorting process is characteristic of algorithms like merge sort, which efficiently handle large datasets by breaking them down, leading to an O of n log n time complexity. This O of n log n sorting, combined with efficient filtering, allows Netflix to provide instant recommendations, making sure you see relevant content quickly. Banks use O of log n data structures to keep transaction processing fast, even at massive scale. This systematic search by continually dividing the remaining possibilities in half is what gives binary search trees their O of log n efficiency, meaning operations remain fast even as the number of transactions grows exponentially. This logarithmic efficiency ensures that inserting new transactions scales incredibly well, preserving system responsiveness even with a massive increase in data. But there's always a trade-off. Hash tables use extra memory to achieve O of 1. Lookup. That's called the space-time trade-off. You trade space for speed. Sorting algorithms that run in O of n log n time often use O of n extra memory. Sorting in place saves memory but is slower. The question isn't which algorithm is best. The question is, which trade-off fits your use case? Let's return to our e-commerce search. Version 1 used linear search. It was simple but slow. Version 2 switched to a hash table. Search became instant, but we had to use more memory to store the index. That memory cost was worth it, because fast search is critical for user experience. Big O thinking helped us make that decision intentionally. It's not about finding the perfect algorithm. It's about predicting how your code will behave at scale and making smart trade-offs before your system breaks. That's the real power of Big O notation.